Okay, let's begin.
Okay. Good evening, everyone. The paper I present today is the FLTrust Byzantine-robust Federated learning via trust bootstrapping. And the first part is the motivation. Federated learning is an emerging distributed learning paradigm on decentralized data. However, due to its distributed nature, federated learning is vulnerable to adversarial manipulations on malicious clients, which could be fake clients injected by an attacker or an genuine clients compromised by an attacker. For instance, malicious clients can corrupt the global model while poisoning their local training data, which is known as the data poisoning attack. All their local model updates sent to the server, which is called the local model poisoning attacks. The corrupted global model makes incorrect predictions for a large number of testing examples, or it predicts attacker-chosen target labels for testing examples. To defend against poisoning attack, the machine learning community has proposed some Byzantine-robust federated learning methods. These methods use Byzantine-robust aggregation rules. The key idea of the Byzantine-robust aggregation rules is to remove outlier local model updates before aggregating them to update the global model. Under some assumptions, such as the client's local data are IID, or the loss function is smooth, and so on, these methods can even bound the change of global model parameters caused by malicious clients. However, the existing methods are insecure. Recent studies show that existing Byzantine-robust methods are still vulnerable to some strong attacks. For example, the local model poisoning attacks and the backdoor attacks. The fundamental reason is that they have no root of trust. In particular, from the service perspective, every client could be malicious. This paper proposed a new Byzantine-robust federated learning method called FLTrust. Instead of completely relying on the local model updates from clients, the server itself bootstraps trust in FLTrust. Specifically, the server manually collects a small clean training dataset, which is called root dataset for the learning task. The server maintains the model for the root dataset, which is called server model, just like how a client maintains a local model. In each iteration, the server assigns trust scores to the clients based on the similarities between the client's local model update and the server model update. And the server aggregates the client's local model updates to obtain a global model update based on the trust scores. This global model update is used to update the global model. So the next part is the design of the FLTrust. As we all know, federated learning iteratively performs the following three steps. The step one is the server sends the global model to the clients. Step two is the training local models. And the step three is updating the global model by aggregating the local model updates. FLTrust follows the general three steps of federated learning. However, it's different from the existing federated learning methods in step 2 and 3. Specifically, in step 2, the server also trains a server model by fine-tuning the current global model using the root dataset in FLTrust. And in step 3, FLTrust considers both the server model update and the client's local model updates to update the global model. So the new aggregation rules considers both the directions and the magnitudes of the local model updates and the server model update to compute the global model update. An attacker can manipulate the directions of the local model updates on the malicious clients such that the global model update is driven to the direction that the attacker desires. Without the root of trust, it is challenging for the server to decide which direction is more promising to update the global model. However, in FLTrust, the root trust originates from the direction of the server model update. In particular, if the direction of a local model update is more similar to that of the server model update, then the direction of the local model update may be more promising. You can consider the two clients which local model updates are G1 and G2. The server model update is G0. G2 is less similar to the server model update G0, so it is more likely come from a malicious client. And the FLTrust uses the cosine similarity to measure the direction similarity between a local model update and the server model update. However, the cosine similarity alone faces a challenge. Specifically, if a local model update and the server model update are in opposite directions, their cosine similarity is negative, which still has negative impacts on the aggregated global model update. So, FLTrust excludes such local model updates from the aggregation by clipping the cosine similarity. In particular, the trust score is defined using the ReLU operation, where the TSI is the trust score of the local model update GI, and the CI is the cosine similarity between GI and the server model update G0. Rho x equal to x if the x is greater than 0, and the rho x equal to 0 otherwise. You can see for client 2, we compute the cosine similarity between G2 and G0. Since the C2 is negative, the trust score becomes 0. And an attacker can also scale the magnitudes of the local model updates on the malicious clients by a large factor such that they dominate the global model update. Therefore, FLTrust normalizes the magnitude of each local model update. Without the root of trust, it is challenging to decide what quantity we should normalize to. However, the server has the root data set to bootstrap trust in FLTrust. Therefore, FLTrust normalizes each local model update such that it has the same magnitude as the server model update. You can see GI is the local model update of the ith client in the current iteration, and the G0 is the server model update. Note that the normalization also enlarges a local model update with a small magnitude to have the same magnitude as the server model update. This is based on the intuition that local model updates with small magnitudes are more likely from benign clients. And thus, enlarging their magnitudes helps reduce the impact of the poisoned local model updates from the malicious clients, which can lead to a better global model. And the experiments later will show this. And the average of the normalized local model updates weighted by their trust scores are used as the global model update. C is the global model update. Note that if the server selects a subset of clients in an iteration, the global model update is aggregated from the local model updates of the selected clients. In principle, the server model update can be treated as the local model update with a trust score of 1, and the global model update can be weighted average of the client's local model update together with the server model update. However, such variant may negatively impact the global model because the root dataset is small and might not have the same distribution as the training data. So So the server model update derived from it has a trust score of 1, which can reduce the contributions of the benign client's local model updates. And also the later experiments will evaluate. Here is the aggregation rule. And the next part is the security analysis. The security analysis shows that under the 3 assumptions shown on the slides, the difference between the global model learned by the FLTrust and the text and the optimal global model is bounded. And the proof can be concluded as follows. Suppose the 3 assumptions hold and the FLTrust uses RL equal to 1 and the beta equal to 1. And let alpha be the combined learning rate. The first lemma is for an arbitrary number of malicious clients, the distance between G and the gradient of SW bounded as follows in each iteration.
Honglu, sorry, what is the RL and what is the beta?
Okay. The alpha multiplied the beta is the learning rate, and here we let the beta equal to 1. We can let alpha be the learning rate. And the RL means the
So I mean, do these 2 symbols appear in your last slide? The RL and the beta? Yeah, because when you introduce some like symbols like this, you need to explain the intuition behind these symbols, right? What are the like indicating?
These 2 symbols are 2 parameters in the paper, and I think it doesn't appear in my slides.
Okay, then what are they used for? So why we need to specify they're equal to 1?
We specify they equal to 1 is to simplify the proof.
So will you like introduce any proof including these 2 variables in your following slides?
No, I think these 2 symbols will not appear in the slides, and then.
Okay, then yeah. So when you introduce something like this, you have to keep this in mind. You need to explain what it is and why we have this, right? And if you don't, if this is not that important for your later on explanation, then you probably need to ignore these variables in your slides. Okay.
Okay.
Otherwise, you have to explain them in detail.
Okay. We said these 2 symbols as one is to simplify the proof. It's just 2 parameters in the paper.
But you have to, when you mention the 2 variables here, you have to explain why we have to set it out like a 1, right?
Okay.
So do you still remember the 2 variables and why and how we use these 2 variables to do the proof?
I didn't remember what the RL is, and the beta multiplied the alpha is the learning rate in the paper.
So the beta times the RL is the learning rate.
Yeah.
Then why we need to have 2 variables to describe the learning rate? The alpha is the learning rate, right? The combined learning rate.
In the paper, it said the alpha times the beta is the learning rate, and here to simplify the proof, they set the beta equal to 1 and let alpha be the learning rate.
So I still don't know why we specify them to be 1. Can you explain why? You may quickly take a look at the paper.
Okay. Oh, okay. The beta is the local learning rate, and the RL is the number of the local iteration.
So why we set the local iteration is like 1 is for simplicity, or and the local learning rate is 1. It's I don't know.
The paper just set the RL equal to 1 and the beta equal to 1, and he didn't explain it. And I think it may be to, because the proof is compromised, so it may be to simplify the proof.
Okay. Okay.
The paper just set the 2 symbols as equal to 1, and he didn't explain it.
Yeah, I believe it's for like the simplification of the proof or something. Yeah, we can discuss this later. You can continue.
Okay. So this is the lemma 1, and the lemma 2 is based on the assumption 1. If we set the learning rate as the alpha equal to some special value, we can have the following in any global iteration. And the lemma 3 is based on...
Can you give us more details about the lemma 1, 2, 3? So what is the intuition behind the lemma 1, 2, 3? Okay, so why we have such like a equation here, and what is the purpose for this lemma?
All the there are 4.
Can you go back to the last page, the lemma 1? Yes. So can you explain it a little bit about this? What is the g, minus the gradients of the and it's less than the right side of the equation.
The G0 is the G0 is the the G0 is the server model update, and the G is the global model update. And the FW is the experience. The FW is the expected loss function. So the lemma 1 to 4 are used in the proof of the the difference between the global model and the optimal global model is bounded. In the proof of this, the authors use the lemma 1 to 4. So here I will introduce the lemma 1 to 4, and finally I will introduce the difference between the global model learned by the FLTrust and the optimal global model.
So the FW here is the expected gradient calculated by the new aggregation rule, right?
Yeah.
So which means it's the FLTrust aggregation rule, and we are using the G2 minus this indicating. So every round we can have a bound over the update of the global model.
Yeah.
And what is the next the lemma 2?
I think the lemma 2 and the lemma 3 and the lemma 4 is just to adjust the lemma used in the final proof. So I'm not
but you have to give us a more detailed explanation about this lemma and the purpose of this lemma, right? Why we want to have this step. I don't need you to prove, okay, this equation, the formula 2 is correct, but you have to, understand why we have this step and what is the objective here. So what is the W star here?
W star is the optimal global model.
And what is the meaning of the left turn? And what is the meaning of the right turn?
I think I should read it more carefully after.
You have a lot of time to read the paper, okay? I'll give you a lot of time here.
Yeah.
Yeah, but this is not what I expect.
The proof of the paper and the writer just wrote the lemma 1, lemma 2, lemma 3, lemma 4, and they just
because the author expects you can understand it. Okay. Okay. You can continue.
Okay. So next is the lemma 3, which is based on the assumption 2. And the lemma 4 is based on all the 3 assumptions. And with the lemmas above, we can prove that the difference between the global model learned by the FLTrust and the optimal global model W star and the null tax is bounded. So here is the security analysis. And the next part is the adaptive attacks. So when an attacker knows the FLTrust is used to learn the global model, the attacker can adapt its attack to FLTrust. Notice that the local model poisoning attacks can be formulated as an optimization problem, and is applicable to any aggregation rule. And here, A is the aggregation rule of the federated learning method. an attacker can construct an adaptive attack to FLTrust by replacing the aggregation rule A as the aggregation rule of the FLTrust in this optimization problem. So we can have adaptive attacks. The third part of the paper is the evaluation. The paper uses multiple data sets from different domains in our evaluation, including file image classification data sets and the human activity recognition data set. The paper considers both data poisoning attacks and the local model poisoning attacks. For data poisoning attack, consider the popular label flipping attack. And for local model poisoning attacks, we evaluate crime attack, stream attack, and the scaling attack, and the adaptive attack. And the global models, for MNIST 0.1, MNIST 0.5, and the Finch MNIST, the CNN is used as the global model, and the LR classifier is used as the global model for HAR. And for the other two data sets, the residual neural network architecture is used as the global model. And this table shows some parameter settings in the experiments, including the number of the clients and some other parameters. And this paper evaluates the method on multiple data sets. And in this slide, we set the MNIST 0.5 as an example. Assume that there are 100 clients and 20 of them are malicious. The server's root data set includes 100 training examples sampled from the MNIST uniformly at random. You can see that the FLTrust has the best performance. And here are the 5 variants of the FLTrust. First, in FLTrust server, the server only uses the root dataset to train the global model. And in the FLTrust V server, the server computes the weighted average of the client's local model updates together with the server model updates. And the server model update trust score is 1. And in FLTrust no review, the server does not use the review. And in FLTrust no null, the server does not normalize the local model updates. And in the FLTrust kernel, the server applies partial normalization. For example, the server only normalizes the local model updates whose magnitudes are larger than that of the server model update. And we can see the results show that the FLTrust outperformed the 5 variants.
I'm sorry. What's this figures denote? Error rates, or what's the metrics?
The metrics is the error rate, and for the scaling attack is the.
Oh, I see.
Yeah.
I see.
Okay.
So Honglu, here for the number, the smaller the better, right? Previous page.
Sorry, can you repeat?
For the numbers in the table, for example, for LF attack, the number, if the number is smaller, that means it's better, right? It can be better
for the no attack, RF attack, crime attack, stream attack, and adaptive attack. The number is smaller, the performance is better. And for the scaling attack, the number is for for the scaling type, it's also the smaller, the performance is better.
So what is a par norm? I understand the FLTrust, they incorporate the normalization rule, but what is a par norm?
It means we only normalizes the local, the part of the local model updates. For example, we can only normalize the local model updates whose magnitudes are larger than the server model update.
Larger than the server, but
it means just normalizes part of the local model updates.
Okay, but in FLTrust, you normalize all the local updates, right? It doesn't matter if the amplitude is larger or smaller than. Oh, okay.
Because the writer convinced that the local model update with less magnitudes have a better performance.
Well, did they explain why, if you normalize every updates compare with you partially normalize, the one larger than the global one, I mean the amplitude larger than the global one, why the fully normalized is better than the partial normalized? I mean, from this table, the difference is very minor, right? So is there any theory or intuitive explanation behind this?
The writers wrote that this is based on the intuition that the local model updates with small magnitudes are more likely from benign clients. So enlarging their magnitudes helps to reduce the impact of the poison local model updates.
Okay. But I'm not that convinced by this explanation. I mean, I know this from their paper, but okay.
Yeah. It's just wrote this tuition and they don't explain it. And I think it can be discussed.
I mean, if the amplitude is much larger than the global updates, right? So either is the honest user is kind of a malicious user. Probably their contribution for next round of global updates will be high, right? We can understand that. If you normalize that, probably you reduce the impacts of those updates. But just in case, if their amplitude is smaller than the global one, I didn't say, it's hard to say normalize bring benefits or bring certain kind of negative impacts. You know what I mean, right?
Yeah. When I read the paper, I have questions about it too. And in the paper, the writer does say that with less magnitude, the update may come from more likely come from benign clients.
Well, it's not necessarily true. If I'm an honest user, I can still probably my magnitude is smaller than the global one. It's still possible. But anyway, okay. Thank you.
Okay, let's go on.
Yes, please.
Next part is the experiments about the different parameters. And here is the experiments evaluates the impact of the number of the iterations. And the next is the experiments evaluates the impact of the root data size. In other experiments, they choose the size the root data size as the 100. And this experiment considered the number of the clients. And here is the friction of the malicious clients. We can see in FLTrust, the testing error rate raises greatly after the friction of the malicious clients is greater than 90%. And the last part is the discussion. First one is the poisoned root dataset. Because FLTrust requires a clean root dataset and may not be robust against the poisoned root dataset, the root dataset may be poisoned when it is collected from the internet. However, since FLTrust only requires a small root dataset, so the service provider can collect a clean one by itself or asking its employees to generate and manually label a clean root dataset. And the second is the adaptive attacks and the hierarchical root of trust. The paper considered an adaptive attack where extending the state-of-the-art framework of local model poisoning attacks to FLTrust. And there may exist a stronger local model poisoning attacks to FLTrust, which is future work to explore. And also, it's an interesting future work to consider a hierarchical root of trust. For instance, the root dataset may contain multiple subsets with different levels of trust. The subsets with higher trust may have a larger impact on the aggregation rule. And this paper proposed and evaluate a new federated learning method called FLTrust to achieve Byzantine-robustness against the malicious clients. The key difference between the FLTrust and the existing federated learning method is that the server itself collects a clean small training dataset to bootstrap trust in FLTrust. And the evaluations on 6 datasets show that the FLTrust with a small root dataset can achieve Byzantine-robustness against the large friction of malicious clients. Thank you.